Okay, so we've got a calculus question here, and we're going to try and solve this integral and try and find y of x. So y, that is a function of x. So x is our independent variable and y is our dependent variable because it depends on x. Now our parameters are when x is 2, so y of 2 is minus 5 over 4, and when x is 4, y of 4 is minus 19 over 4. That's the only information we're given, as well as this integral here. Now you'll see here, got the range of, the parameters of integration which we're given here, and integrating with regards to x, and we've got a y prime, we've got a y, and we've got another y here. And notice that this y here is squared. Now we've got in here a quadratic, so we need to try and get that quadratic out of there and maybe onto another side of the equation and maybe solve for the quadratic. That's going to be our kind of technique here. Now when we've got an integral in this form, the Euler Lagrange equation is going to be the way forward. So the Euler Lagrange equations, I'll just put it like that. For a function in this format, so we've got we've got x, we've got y, and we've got y prime. So let's just, and y prime. That's the format of our functional. So the Euler Lagrange equations will then be the derivative with respect to x of the partial derivative of s with regards to y prime. So that's one term there, and we subtract this from the partial of s with regards to y and set that to 0. That's going to give us the path to give us some possible solutions to solve this. So, well, partial with regards to y prime and the partial with regards to y, and then taking derivative with regards to x, we can do that for this functional. So let's start off by taking this partial here. So partial of s with regards to y prime, that's pretty much straightforward. We can do that from here. There's only one term with a y prime in it, so derivative of y prime squared is just 2y prime. So 2 comes to the front, reduce the power by 1, 2y prime. And then the partial with regards to y, that's going to be a little bit more involved. So the y prime squared is not included. This one we can do. So multiply by the power, so that's 2 times 4 is 8. And then the y will stay, and that's to the power of 1, obviously reducing the power. And then this one here, we've got the quadratic multiplied by 2 multiplied by y. So for the derivative of that as a partial with regards to y, all we're going to do here is just drop this y. So here we're going to add, so it still stays as a positive, 2, and then the quadratic, 2x squared plus x plus 2. So now we can just continue with this Euler Lagrange equation. So this partial here with regards to y prime, that's this one. So we just bring the 2y prime down and then subtract the whole of this one. So now we're going to subtract, so this is a positive here. So now as we're subtracting, that's going to become a negative. So minus 8y. And then we're going to subtract again. So this positive will now become another negative. So minus 2x squared plus x plus 2. And then we set that to 0. Okay, this y prime, this is a function of x. So the derivative of that will just become y double prime. So we can take care of this term here and just write this as 2y double prime. So that's the derivative of y prime, minus 8y minus 2 times r quadratic and set that to 0. Okay, just a little bit of simplification. We can divide all these terms by 2, including the 0, which obviously is not going to change. So then we're left with y double prime minus 4y minus 2x squared plus x plus 2. We can set that to 0. Okay, so now we're definitely in the format now of some sort of second order linear differential equation, because we've got y double prime making it second order, and we've got minus 4y minus this quadratic here. So we can rewrite this as y double prime minus 4y equals, so bring this over to the other side, so I'll keep that in the brackets to keep it all together. So now we've got a second order differential equation in that format. Okay, so now there is a way we can use to solve this. So I'm just going to write this up here underneath these boundary conditions. So the format for y of x, which is what we're trying to look for, let's just write that up here. Y of x, that will be then split up into 2 calculations. The complementary function, equals the complementary function of y of x, so as a subscript c, plus the particular solution with regards to x, that's yp of x. Okay, so that's the first stage. Now, okay, so looking for our complementary solution, first thing we need is what's called our auxiliary equation. So what we do is now we just ignore this quadratic, and what we're interested in is y double prime minus 4y equals 0. So just imagine that for now, just ignoring this. Now we turn this into what's called a complementary, an auxiliary function. Now if you check the link below, there'll be some links into the theory as to how the auxiliary function works. But for this video, I'm just going to go straight into it and just show you. The y's you just exchange for functions of lambda. So here, when it's a y double prime, that will become lambda squared. Here, when y is to the power of 1, that will become a lambda to the 0. So basically it just becomes lambda squared minus 4 equals 0. That's all we need now for our auxiliary function. And then we just do here is to solve for lambda. So therefore lambda equals plus or minus 2. So that, bring the 4 onto the side, lambda squared equals 4. So therefore lambda equals the square root of 4, which is plus or minus 2. So I'm now going to write that up on here because that's important for us. Lambda equals plus or minus 2. Okay, now I'm going to rub this off the board, and then we're going to go to the next stage and how to work out the complementary function. Now our complementary function, so y c of x, takes the form in this kind of format. Now this is the format I'm going to use. I'm going to use alpha y1 of x plus beta y2 of x. Now this is the general accepted way of beginning your calculation here. So now what I want is 2 linearly independent functions I can put in here for my y1 of x and my y2 of x. Now there's more than one way of doing this, but the way I'm going to do it on this one is I'm going to use sinh, the hyperbolic sine function. So we've got alpha times sinh, and then for our input for sinh we use our lambda, and what we do is we use the absolute value of lambda. So I'm just going to put an absolute value here of the lambda because we've got 2 versions, plus or minus. So I'm going to use the absolute value, so I'm going to use the positive, and then we multiply that by x minus our first boundary value, which is 2. And then we're going to add on that beta times sinh again. And again, I'm going to use the absolute value of lambda. And then this time, the other boundary value, which is 4. So x minus 4. Okay, so I'm just going to rewrite that again. So now I've got alpha sinh of lambda, absolute value, which is 2. And then x minus 2. Just get the right amount of brackets. And then beta times sinh lambda again, which we know is 2, absolute value, and then x minus 4. So we know that these two are going to be linearly independent because there's going to be different values for x different values of the input when we subtract 2 or subtract 4. Okay, now moving forward on this, there's a couple of trig identities we're going to need to remember. First one is really simple. Sinh of 0 equals 0. So let's just, that's pretty straightforward. You're going to know that one. The next one you may not know is that the sinh of a negative number, so for example, I'm going to use, let's use k. Sinh of minus k equals minus sinh of k. So this minus can come out and that works for sinh. Okay, so that takes care of our complementary function. Now we need to find the particular solution. So now we need the yp of x. Okay, now yp of x is a little bit different. So how are we going to set that up? So it equals our result of our Euler Lagrange equation from before. So we had y double prime. This time I'm going to use a subscript p because we're trying to find a particular solution, minus 4y subscript p, and that equaled our quadratic. Okay, now we've got to try and find a solution for x squared, x, and coefficient. So to do that, I'm going to break down these coefficients here for our x squared, x, and our coefficient, and we're looking for something that looks a little bit like this. So we're looking for an a0, and that's just a coefficient, and then we need for x, so a1 of x, and then for x squared, a2 x squared. So my subscript is equal to x to the power of that subscript, so it's easy to follow. Okay, so now trying to solve for this kind of format for this and using this. Now our y double prime, we know that's going to give us a value of 2 for our a2. So now we're going to be left with 2a2 and subtract 4 times. Now our y particular solution is going to be of this format. So I'm going to plug that in here for our yp. So a0 plus a1x plus a2x squared. So I'm going to write this the other way around so it's easy to follow. a2x squared plus a1x plus a0. That's our particular solution format, and that's going to equal 2x squared plus x plus 2. So now you can see now why this a2 becomes 2, because if we take the second derivative of this, you're going to lose these two terms, and your x squared will become 2x, and then 2x differentiates into 2. So therefore we've got the 2 for the a2 here. Okay, so now I'm going to multiply out by this 4 here. So now I've got 2a2 minus 4a2x squared minus 4 again, a1x, and minus 4a0, and that equals 2x squared plus x plus 2, thus giving us our particular solution. Okay, now let's solve for these A0, A1 and A2 here. We should be able to do that by using this particular solution. So let's have a look at the x squareds. So 2x squared is minus 4a2 x squared. So therefore we've got minus 4a2 equals 2. So that takes care of that. And then we can solve for a2 from there. So a2 looks like a 9. a2 equals 2 divided by minus 4, which is minus 1/2. So that takes care of a2. Let's have a look now at a1. So a1 is a function using x, that's a coefficient there. So minus 4a1 equals 1. So therefore we can say that a1 equals minus 1 over 4. 1 divided by minus 4. Okay, now let's have a look at the constants. Now this a2 came from y double prime, but now it's a constant coefficient because there's no term x here. So now we've got 2a2 minus 4a0 equals just this 2 here. Now we've already worked out what a2 is, so that's minus 1/2. So we've got 2 times minus 1/2 minus 4a0 equals 2. This we now know is minus 1. Bring to the other side, we've got minus 4a0 equals 3. a0 equals minus 3 over 4. Divide both sides by minus 4, and that's what we get. So now let's write these coefficients in here. So we've got a0 is minus 3 over 4. a1 equals minus 1 over 4. And a2 equals minus 1/2. Okay, now what we can do is we can use these now in this in our particular solution for y of x and our complementary solution for y of x, use the boundary conditions, and then using these we can solve it. So now I'm going to rub this off the board and then go on to that stage next. Okay, so now putting it all together. So just remembering what we'd already done, we got y of x equals our complementary function, so that's alpha, sinh of lambda, which was 2, then x minus the lower value of the of our boundary, which is 2, and then add beta times sinh of 2 times x minus the upper boundary, and then after that we add on to that our particular solution. So then we add on to that our values here plugged into this function here. So then we've got x squared, which is a2, so that's minus 1/2 x squared plus minus 1 over 4 for x. So then I'm going to change that to a minus sign. So minus 1 over 4x. And then our coefficient is minus 3 over 4. Okay, that's our function that we're going to use here. And now we're going to use our boundary conditions. So when x is 2, this should equal minus 5 over 4. So y of 2 equals alpha sinh of 2 times x minus 2. So I'm going to write a 2 in there. 2 minus 2 plus beta sinh 2 times 2 minus 4. And now just plug in 2 for this x. So that's minus. So x when it's 2 is 4. So that's minus 4 over 2. X is 2 here, that's minus 2 over 4. So that's minus 1/2. And then minus 3 over 4. Okay. Now we got our trig identities here. So this one we know is just going to be 0. So this alpha will disappear. Now we'll be left here with our beta of sinh of 2 times minus 2. So so that becomes sinh of 4, so that becomes a minus as well. And then this we need to evaluate. So now we're left with y of 2 equals beta sinh. Now this, using this identity, becomes 4, but we now need a minus sign here, as we did here in our identity. So minus 2, minus a half, minus 3/4. So if we work that out, we're going to get minus 13 over 4. So that's just 3 1/4. Okay, and when we've got y of 2, this equals minus 5 over 4. Okay, so now we can solve for our beta. So we can say y of 2 equals, we're now left with minus beta sinh of 4. And now bring this onto the other side. So now we're going to add 13 over 4 to minus 5. So that's just going to leave us with 2. So that equals 2. Now distribute the minus and divide both sides by sinh of 4. So y of 2 equals beta, which is then going to give us 2 over sinh of 4. So that's going to give us our beta value. So now we need the value when we've got y of 4. So that's minus 19 over 4, and plug in 4 into all these. So y of 4 equals alpha sinh 2 times 4 minus 2 plus beta sinh 2 times 4 minus 4 plus, now we're going to plug in 4 now for all these x's. So 4 squared is 16, so that gives us minus 16 over 2. 4 over 4 gives us 1, so that's minus 1. And then minus 3 over 4. Okay, now we've already worked out what beta is, but here we've got a sinh of 0 situation, so that term cancels out. So now we're left with y of 4 equals alpha sinh of 2 times 2. So obviously that's going to be our 4. Plus, now we've got minus 16 over 2, which is minus 8. Minus 1 is minus 9. And then minus 3/4. So that's minus 39 over 4. And then using our boundary condition, we've got minus 19 over 4. Okay, now let's do as we did before. Alpha sinh of 4. Then we've got plus minus 39 over 4. Let's bring that on the other side. So we add 39 over 4 to this. So that's just going to give us 5. So that equals 5. And now we can say that alpha equals 5 over sinh of 4. Okay, so we've got these two values here now. Let's just write them up here. So we've got beta equals 2 over sinh of 4, and alpha equals 5 over sinh of 4. Not forgetting our minus sign. I've just missed out the minus sign here. So that's a minus, minus. Okay, so I'm going to rub these out and I'm going to put up my final solution for what I think this function should be. Okay, so now plug in all the alpha and beta into this. It's going to give me my final function for y of x. So I'm now going to say y of x equals alpha, which is 5 over sinh of 4. So it's sinh of 4. And then we multiply this 5. Make sure this 5 doesn't look like an S. And then we've got sinh of 2 times x minus 2. And then we're going to add, but I'm going to change that because I've got a minus sign here for my beta. So I've got minus 2 over sinh of 4. And then I've got sinh of 2 times x minus 4 on the top here in our denominator. And then I'm going to add onto that my quadratic here, which I'm now going to change this plus to a minus and distribute the minus into it just to make things look a little bit neater. So minus 1/2 and then x squared, so that 1 can disappear. Now I'm going to use my minus again, so I'm now going to have minus x over 4 and minus again minus 3 over 4. That is going to be my final solution for my y of x, to solve for y of x with these boundary conditions, which was my original question. Okay.